Hey Stephanie, so I am going to go ahead and record this. It's not going to be as clean or put together as some of the other ones, but this will get you what you need to get the content that you would have missed on Monday. So this chapter is on covalent compounds, and if you remember right, when we were talking about ionic compounds, we were talking about a transfer of electrons, and those were between metals and nonmetals. So you have, in this example, sodium that has that valence electron that it wants to get rid of, and you have chlorine that wants to take that electron, and so sodium is just going to give up that electron to chlorine. So you have that complete transfer of electrons in an ionic bond. With covalent bonds, on the other hand, you have things that are sharing electrons. So if you remember right when we talked about ions, you have an unequal number of protons and electrons, and so there's a charge, and ionic compounds have oppositely charged ions. So if I have a positively charged ion like sodium +1 and a negatively charged ion like chlorine -1, those things are going to have an attraction to one another and form that compound. And then the cations are the positive ones and the anions are the negative ones. When we have covalent compounds or molecular compounds, you can hear it either way, these are going to be formed when two nonmetals combine or when a metalloid bonds to a nonmetal. For our purposes, we're going to focus on when two nonmetals combine. When that happens, so when two molecules decide to share those electrons, we call that a molecule. So in this case right here, you can see, okay, our hydrogen, which is a nonmetal, has one valence electron, and then this hydrogen atom has one valence electron, but they both want to see two because that gives them that full outer shell. And so what's going to happen is they are going to share both of those electrons, like you can see here, and that forms what we call a covalent bond. And remember, sharing is caring and caring is covalent. So that's how I remember covalent is a sharing of electrons. Kind of silly, but I don't know, it stuck with me for some reason. So when you have covalent bonds, again, it's that sharing of electrons, like you can see with this example of hydrogen. And when you see a bond in a Lewis structure, which we'll get to in a moment and we'll really focus on today in class, but a covalent bond is a two-electron bond in which the bonding atoms share those valence electrons. And a molecule then is a group of atoms that are held together by those covalent bonds formed from those shared electrons. We can also have unshared electron pairs. We can call those, for our purposes, I usually refer to them as lone pairs of electrons. You can also call them non-bonded electron pairs. That's perfectly fine as well. But in this case, we have hydrogen with its one valence electron and fluorine with its 7. But if this hydrogen completely gives up, scratch that, sorry. If this, so this hydrogen has that 1, this fluorine has that 7, well, if they share those, then they can form a covalent bond, and each time you see a line, that represents 2 electrons. So right here, this 1 electron came from hydrogen, this one came from fluorine, and now they're sharing in that bond. On fluorine, though, we still have these 6 valence electrons, so we would say we have 3 lone pairs, 1, 2, and 3. So if we count electrons around each of the ones, hydrogen sees 2 from this bond, so it's happy with those 2. Fluorine sees the 2, 4, 6, and 8, so it has that full octet, and it's happy as well. You can use Lewis structures to help you visualize how atoms are connected and also where all of those valence electrons are located in that molecule. So when we look at something like methane, carbon has 4 valence electrons, so it's 1, 2, 3, 4, and then hydrogen each comes with 1 valence electron, and so you can see that carbon is going to want to form 4 bonds. So this is the structure right here for methane, which is CH4. if we look at something like ammonia, this nitrogen is going to have 3 bonds, 1, 2, 3, to the 3 hydrogens, and then it has this 1 lone pair. Now this 1 lone pair is going to influence the geometry, which you can see right here, but that's something that we're going to get into today. So, yeah. For water, you have these 2 bonds, and then you have the 2 lone pairs, and again, that influences the structure. But you can see in all of these cases that each of these has a full octet, except for hydrogen, which has that duet because it's too small to see 8. Yeah, let's see here. So we talked about covalent bonds forming between 2 nonmetals, but the periodic table is a super useful tool to predicting how many bonds a particular atom will want to have. Atoms with 1, 2, 3 valence electrons are going to form 1, 2, 3 bonds respectively. Atoms with 4 or more valence electrons form enough bonds to give an octet. So for these atoms, the formula you can use is the predicted number of bonds is going to be equal to 8 minus the number of valence electrons. So if we're talking about nitrogen, for example, nitrogen is in group 5 on the periodic table, so 8 minus 5 is going to give us 3, and that's how many bonds nitrogen is going to want to form. So this kind of reiterates that point. Hydrogen is in group 1. It's too small to have more than the 1 bond. So anytime you see hydrogen in a compound, know that it is not going to be found in the middle of the compound. It'll always be on the periphery because it can't connect 2 things because it doesn't have enough room to see that many electrons. So hydrogen is always going to form 1 bond and have no unbonded electrons. Carbon is in group 4 and is going to want to see 4 bonds. So there's the 1, 2, 3, 4. If we think about nitrogen being in group 5, it's going to want 3 bonds and it'll have 1 pair of unbonded electrons. So 1, 2, 3 for the bonds, and then our lone pair of electrons. So you can see that each one of these bonds represents 1 electron coming from nitrogen plus the 1 electron coming from whatever it's attached to. And so you can see 2, 3, 4, 5 for nitrogen, those valence electrons. But when you count how many electrons it sees, it's going to see all of the electrons from these bonds. So we say it sees 2, 4, 6, and 8. If you continue on to oxygen, oxygen's going to want 2 bonds with 2 lone pairs. The same for sulfur, which is also in that group. You'll see that sulfur is kind of an exception because as you go down the periodic table, remember that we have those D shells. And the D shells mean that our electrons can start, they have a little bit more freedom to do things. And so things get a little bit weird, but we'll get to that. But in general, group 6 is going to want to see 2 bonds and 2 lone pairs. When you get to group 7, we have the halogens, and they're always going to want to see that 1 bond and have 3 lone pairs. So that could be either fluorine, chlorine, bromine, or iodine in that case. So a molecular formula is going to show the number and identity of all of the atoms in the compound, but it doesn't tell you which atoms are bonded together. So if you have something like, I don't know, CH2O, which is the formula for formaldehyde, that doesn't tell you anything about what is connected to what or where the lone pairs are. But it's useful because it shows you, if you're looking at, say, CH2O, it tells you that there's 1 carbon, there's 2 hydrogens, and there's 1 oxygen in that compound. So it's useful to get you started, but it doesn't tell you how they're connected. A Lewis structure, on the other hand, is going to show how everything is connected, as well as where all of the bonding and non-bonding valence electrons are, which is going to be really important when you get into things like chemical reactions and what's going to react with what and why, how things are going to interact. So, for example, will something dissolve in water or won't it? All of those things are really important in understanding the chemistry of individual molecules. So when you draw Lewis structures, the first point to make is that you're only going to draw the valence electrons. So these are the electrons found on the outer shell, right? Those are the electrons that are furthest from the nucleus, so they're going to feel the least amount of attraction to one another, and so that leaves them to kind of be free to participate in bonds and participate in reactions and things like that. So when you're drawing these structures, you're going to give every main group element an octet of electrons, with the exception being hydrogen, because again, hydrogen only wants to see those 2 electrons. So when you draw your structure, you're going to want to arrange the atoms that you think are going to be bonded to one another, and then start drawing the rest. So you're going to want to put halogens and hydrogen on the periphery, so on the outside of the molecule, because they can only form one bond. And so you're not going to arrange things like this, where carbon is seeing these 3, and then this hydrogen is kind of in the middle, because if this hydrogen has to bond here and here, it's going to see too many electrons, right? So what makes a lot more sense is to arrange those hydrogens around the carbon. Then what you're going to do is use your common bonding patterns to arrange the atoms. So we know, for instance, that carbon wants to see 4, and so we're going to place 4 things around it. Where nitrogen, we know, wants to see 3, and so we're going to start arranging our atoms so that nitrogen sees 3 things that it can bond to. On the other hand, we wouldn't want to put that other hydrogen here, because nitrogen in this case would see 4 bonds where this carbon would only see 3, and that's not what they want, and so it makes a lot more sense to arrange it that way. Then what you're going to do is count the valence electrons. I actually do it a little bit differently than what the steps in the book recommend. So in the book, they recommend that you add up all of your valence electrons to start with, which is fine. You can do that with the other method as well. But what I recommend is just drawing all of the valence electrons in. To me, it's a lot easier to visualize than it is to count and then start filling things in that way. And I'll kind of, hopefully you'll be able to see what I mean. So for me, I would start by drawing the valence electrons around each element. I apologize for how messy this looks. This is the best I could figure out. So once you do that, so hydrogen has 1 valence electron, so you can see each one of these has its 1. Carbon, being in group 4, has its 4 valence electrons, and then chlorine, being in group 7, has 7 valence electrons. Once you have those valence electrons in, you can start connecting your atoms. Here we go. Okay, so we've arranged our electrons around the atoms, and now what we're going to do is say, okay, I have a molecule, so I know everything has to be attached somehow, right? Everything has to be connected. So what you're going to do is bond everything, and then you are going to make sure that everything is satisfied, has a full octet, and if not, we need to pay attention to where our lone pairs are. So for me, I would look at this structure and I would say, okay, my carbon has to be connected to each thing. So there we go. It's all connected. And now we would go ahead and count how many valence electron each thing sees. So if we look at hydrogen, this, again, remember a bond is going to represent 2 electrons. So this hydrogen sees 2 from this bond, this one sees 2 from this bond, and this one sees 2 from this bond. If we look at carbon, we see 2, 4, 6, 8, so that's that octet. And if we look at chlorine, we see 2, 4, 6, and 8. Everything has a full octet, everything's happy, and so this would be the correct Lewis structure for CH3Cl. There are cases where you need to have a double bond or a triple bond. So if we think about oxygen on the periodic table is in group 6. And so what that means is it has 6 valence electrons. It needs to see 2 more. And so if we look at our oxygen, and we can see 2, 4, 5, 6 would come from that, and 2, 4, 5, 6 would come from this. That bond, by making the bonds, now this oxygen sees 2, 4, 6, 8, and this one sees 2, 4, 6, 8. You can see that if we didn't have a bond, each of those oxygen would only see 7, which is super unstable, and so what they do instead is form that double bond. In the case of nitrogen, we know nitrogen wants to see 3 bonds, so it makes sense that this would happen. And if we count the electrons around each, 2, 4, 6, 8, 2, 4, 6, 8, we can see that both of those nitrogens are happy. So when we think about these things in nature, right? So if I have oxygen, right? It's not just one atom of oxygen that's floating around by itself. Atoms are so small that when there's one, there's going to be more of that thing around. And so what that means is each oxygen having 6 valence electrons is going to be around other oxygens that also have 6 valence electrons. So instead of existing as just a single species, what they do is they pair up, and we call that a diatomic molecule. When a single atom bonds to another atom of itself, we call that diatomic. There's 7 elements on the periodic table that form those diatomic bonds, and they are in the shape of a 7 on the periodic table. Let me see if I can find a periodic table. Sorry, I'm probably making you dizzy here. Let's pull up a periodic table. Okay, so the diatomic molecules are going to be hydrogen, and then there's nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. The nice thing about this is it forms a 7 on the periodic table, and there are 7 of them. Hydrogen being that oddball is kind of off to the side, doesn't fit into the 7, but hydrogen rarely follows the patterns that apply to everything else. So we have hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those are our diatomic molecules. Okay, so if we're drawing the structure for something like C2H4, we can see that the first step is going to be to arrange those atoms. So we have our carbon. We know that these hydrogens can't be in the middle, right? They can only be bonded to one thing. And so when we arrange them, we're going to arrange them so that the carbons are close to one another rather than those hydrogens being in the middle. Next thing you could do is count the valence electrons, or if you are like me, you could just draw them all in. Okay, and then the next thing you're going to do is connect everything, right? So you know that everything has to be connected. So if we draw all of our connections, we can count how many electrons each thing sees. So this hydrogen right here sees 2, 2, 2, and 2. So those hydrogens are all good. If we look at this carbon, it sees 2, 4, 6. So that one's not happy, but this one sees 2, 4, 6, 8. So this one is happy, but this one is not. So rather than leaving something unhappy, it's going to form a double bond instead. So these 2 electrons right here go to form this double bond, and you can see that structure right there. The next thing we did is just practiced drawing the Lewis structure for CO2 and C2H4. C2H4 you just saw in the previous. So what I would do is practice and try to draw CO2 and then find the structure online and double check it. There are a few exceptions to the octet rule, of course. Always exceptions to everything. So with the octet rule, hydrogen we already know is an exception, right? We've seen that multiple times already. The other example is boron. So group 3 elements, 3A elements, there's only one that's a nonmetal, and that's boron. And so boron is an exception to the octet rule. Because that's fairly small, it is perfectly okay with only seeing 6 valence electrons. So the second exception is boron. The other exception, which I mentioned a little bit earlier, is that the third row elements have empty d orbitals available. So that means that they have kind of a little bit more room to work with, to play around with. So elements like phosphorus and sulfur, those are the 2 exceptions that you'll want to remember, although I don't think I will ask you any of these on an exam. But just know that they are capable of seeing more electrons because they are bigger, because they have those d orbitals. All right, the last thing we did was just kind of review those rules. Again, we're going to be practicing drawing these structures, so if it's not quite clicking, that's okay. We're going to see quite a few structures. We're going to practice structures, practice molecular geometries and all of that. So your rules are going to be to choose your central atom. Usually that's closest to the center of the periodic table. If you see carbon, you can almost guarantee that it's that's going to be a central atom. You'll add up the valence electrons from each atom, or go ahead and draw them, and then you can start connecting the dots. So connect the outer atoms to the central atoms, start with single bonds, put lone pairs on your atoms that don't have a full octet, and then if you don't have enough, make double and triple bonds as needed. All right, that is as far as we got in Chapter 4, and so hopefully this helps, but if it doesn't, feel free to let me know if you have questions, and as you know, I'm always happy to answer them.